So Edward, are you ready?
Yeah, I can.
I think it's time. We can get started. So let me just welcome everyone to another one of our KNAW BiophysicsNL meetings. I'm Chase Bruders. I'll be hosting today on behalf of all the co-organizers, which include Greg Stevens, Lida Vailan, and Tom Shimizu. So first, I'd like to introduce our panel members for today's meeting. We have Marjolein Dochtrom from Delft, Lucas Kapitein from Utrecht, and Bella Mulder from Aalmof. So thanks so much to all three of you for joining. This makes the online discussions way more lively and much more interesting. So our audience is also invited to participate in the discussion during the tutorial, which is going to be the first hour today. Feel free to interact. Most of you should be able to actually turn on your mic and ask your questions yourself. Once we shift to the short talks in the second hour, I'll ask everyone except for the panelists to go on mute, and then you can post your questions in the chat and we'll read them out loud for the speakers. All right, so one of today's speakers is Sophie Dumont from UCSF. So she has some constraints in the early morning in her West Coast time zone, so she's joining in later. And therefore, we're going to commence with Eduard Hanetso first. He'll start with his tutorial, followed by his research talk. So just to introduce Eduard, he got his PhD with Jean-François Joly at the Institut Curie and the University of Pierre and Marie Curie in Paris. He spent some years as a postdoc at the University of Cambridge as a Sir Henry Wellcome Fellow and a Trinity College Junior Research Fellow. Afterwards, he moved to Austria and he started as an assistant professor at the IST in Vienna. His theoretical group is interested very broadly in self-organization in biology, from subcellular to tissue skills. So Eduard, we're very grateful that you were willing to join us today and give a talk, and the stage is yours.
Yeah. Well, so thanks a lot for the invitation, first of all, and yeah, it should be fun. I mean, obviously, as Chase says, I mean, you're welcome to ask any question at any point. So actually, for me, it's quite practical that the tutorial is before, because I wanted to talk, I mean, in the research part, I wanted to talk about some recent collaboration we've been working on the question of organoid morphogenesis, so to understand how organoids are shaped from a mechanical perspective. But for this, the basic models that we use are 3D vertex models, so it's perfect because I'll use the tutorial to sort of review, let's say, the past sort of 10 years of the literature on this kind of on using vertex models to understand biological tissues. And I should say straight away that sort of therefore, I mean, in this first hour on vertex models, a lot, if not actually the majority of things I'll talk about is sort of not my own work, right? Things from the literature, and I'll try to not, I mean, and sometimes I might have, I mean, it's a broad field, so I might have forgotten some names, but I'll try, of course, to list a bunch of references for your. I try to list a bunch of references for your interest. So the general questions I want to talk about here is if you think about tissue mechanics and morphogenesis, one of the key questions in morphogenesis is the fact that you start from something which is very symmetric, right, and you end up with things that shows with a lot of patterns. And one of the big questions on the theoretical side, if you think about development of organisms, has been how you do these different steps of symmetry breaking to increase complexity in development. And the paradigm for thinking about this for a long time has been the idea of Turing patterns, which I'm not going to go into the details here, but essentially a biochemical view of reaction diffusion as allowing for the spontaneous formation of patterns through the sort of idealized picture of morphogens, diffusible morphogens cross-reacting with each other and making patterns if they have a different diffusivity. But even though it's not a new idea, I mean, this dates at least from Darcy Thompson at the beginning of the 20th century, there's been a renewed interest in the last 10 or 20 years to think about a more mechanical basis of morphogenetic events, essentially with forces not just being with forces not just being needed to shape locally a tissue, but also to convey information and patterns large scale, and being able to, as its mechanical instabilities themselves, as an organizer of developmental processes. And therefore, as you saw from my talk, what I want to talk about is the type of mechanical of theoretical frameworks that have been used in the past and developed in the past 10 or 15 years to think about these mechanical instabilities and mechanical deformations in biological tissues. So the difference in, I mean, the difference, you can think, if you think about the simplest the simplest deformations of a tissue, you can think in terms of tissue folding or tissue bending, right? You have initially something flat, and the simplest thing you can imagine is you start deforming it in one dimension. You start deforming it out of plane in one dimensions, and you can imagine already that you can imagine quite a few scenarios that give rise to these kind of shapes. And this is something actually that dates back to at least to George Orster in the 90s, that sort of started thinking about a mechanical perspective for these, and started asking, well, what are the kind of scenarios that you can come up with that are consistent with some specific biological data to explain these deformations. And two very broad classes of scenarios that that I'll talk about more actually in the research talk is you can imagine mechanical deformations coming from localized forces that are pre-patterned. So you can think, for instance, if you think about a monolayer, you can think about special cells here that put a lot of forces on the upside, and that tends to generate a spontaneous curvature, and that tends to give rise I mean, these kind of patches of cells encodes, pre-encodes, let's say, a mechanical deformation, which is gonna give rise to this sort of to these out of plane shapes. You can imagine a similarly, let's say, half pattern scenario where you have two tissues, one which grows differentially, one which grows more than the next, but the two are bound to each other, and similarly. That breaks symmetry, that's something that breaks up down symmetry in your entire tissue, and that gives rise through effectively buckling to again a shape that to again a transition from something flat to something curved. But you can also imagine something slightly more emergent, where if you imagine a single tissue which you compress, and that is mechanically stabilized. So if you would press on that beam and there was nothing around it, that's Eulerian buckling. So you would give rise to a single deformation, which a single deformation. However, as I'll go a bit more in detail, if you start sort of constraining, if this beam, for instance, if this tissue is constrained from the top or the bottom, pretty quickly you start getting buckling at a finite wavelength, which is a really simple scenario that has been thought about quite a bit in the last 15 years to explain how from something homogeneous you can end up with a wavelength that really sort of comes from that really is not pre-encoded, let's say, in some way by pre-existing groups of cells. Which is, again, if you think about sort of really ab initio patterning, that's really the kind of scenario, the kind of scenarios that you want. And one of the examples, so again, if you think about these different types of scenarios, hidden in there's already quite a bit of complexity that's being hidden, right? You can think here this is pretty simple. This is Eulerian buckling. But here already in the scenario, you need some cells to be special. You need some cells to regulate. To regulate their mechanical properties differentially up versus down. I mean, you can imagine suddenly that there's quite a lot of machineries. You need to think about the cytoskeleton. You can think already that there's quite a few layers of complexity that you need to put in your model, right? And so one of the things I want to discuss the most in this tutorial is a question that pops up is essentially anytime you want to make a theoretical model, particularly in biology, is what's the level of complexity that you want to put in, right? Because that's if you think about the past literature, if you think about the past literature, you really have a huge continuum of things you can model. You can imagine modeling biology, again, from the point of view of material science, seeing a tissue as an elastic material with a single elastic constant. Or you can think about really detailed modeling of subcellular elements, where you're really interested in sort of individual biochemical pathways that are going on in different cells. And the obvious answer is that different types of, that different types of questions require different types of complexity. But in this talk, in this tutorial, I just would like to start from essentially the simplest thing you can imagine, and ask how can you complexify it little by little, taking into account some of the key features, some of the key features and key structures of in biological materials, basically.
Can I ask something?
Of course.
Eduardo?
Yeah, of course.
In the previous two, these are drawings, right? But you put a scale there, 3 centimeters, 2 millimeters. So yeah. Does it have any meaning here, or is there supposed to be a difference on these different length scales?
Yeah, so I'll actually show in the next slide what I mean. What is this actually? This is so I might just show you exactly what this is. So okay. So here, this is a paper from the Madhavan, from Cliff Tabin and from the Tabin and Mahavan and Madhavan groups, where the question is what explains the looping of the gut. So essentially, this is a gut. A gut. If you think about the gut, it's a tube, right? And initially in development, it's flat, and at some point, it acquires these looping behaviors that enables it to that enables it essentially to be packed to be packed efficiently, right? And so one of the questions you can ask is what gives rise to this looping of the gut that occurs here at the millimeter scale. And one of the most, this is I think a really elegant paper which proposes essentially the way where this looping emerges is simply by coupling two elastic materials, basically. You couple an elastic tube, which is your gut, to a mesentery sheet, which is essentially the surrounding tissue, which is also an elastic sheet. And the very generic things that happen is that as soon as you have two organs, they don't necessarily are going to grow to the same. They're not necessarily going to grow to the same magnitude, and therefore, pretty generically, if you think about two organs, you're going to get mismatches in growth. And if both of them can be adequately described as elastic media, that's going to give rise to residual stresses in your tissue. And so here, this is a very simple picture where if you sew together, and it's actually a mechanical model, an actual mechanical model that the Madhavan group did by just sewing a tube, just sewing a hose to an elastic sheet. This is a completely different scale, but of course the physics is exactly the same. Where the patterns can be derived from just a few parameters, and in all of this instability, and in all of this, and in many of these cases in the field, you can understand the wavelength of your pattern pretty simply because you have very few parameters. The only parameters that you have, the only dimensionless ratios that you can make are the ratios of your two elastic constants. So you have an elastic constant for your tube and an elastic constant for your sheet. So that so you can make a dimensionless ratio out of those. And the second dimensionless ratio you can make is two geometrical quantities. So here, which compares essentially the moment of inertia, the moment of inertia of the tube with the thickness of the sheet here. And so pretty generically, I'm not going to go through what you can do is you can ask what's the energy, what's the minimum of an elastic energy, which is defined as the source as the sum of this tube and this sheet. And again, that just and you can minimize for this, assuming that the two are sewn to each other. So the only constraint you put is that the two are constraints to occupy the same length. And very generically, in this kind of instability, you're going to get you're going to get a length scale which emerges as essentially as a balance, as an energetic compromise, and as a balance of the different elastic modulus. And you can see, yeah.
Just a question about this. So also a question about what is desirable, the desirable complexity here. If I understand this argument correctly, it's all linear elasticity, right? But the actual folds that you ultimately generate in things like the gut are huge. They're quite massive. So do those nonlinearities actually? Do the nonlinearities that could play any role in setting other length scales and things like this, or does it really boil down to just a relatively simple linear elasticity problem?
Well, so that's exactly. So that's no. I think it's a really good. I think it's generally a really good question. I think. I think what's generally assumed is that at least the selection. The initial selection. The initial selection of the wavelength is dictated by this kind of simple linear elasticity measurements, and then of course. At some point, there's going to be. These tissues are plastic to some degree. There's going to be division and proliferation, so you're going to relax. You're going to relax those skills. But that's exactly. So that's actually the next slide I wanted to go back to. I think these kind of models are extremely useful to think about the emergence of patterns, and the cool thing about it is that they reduce to a few parameters. Then what's contained inside those? Actually, in that paper they did measure, for instance, they did measure the elastic constants and the geometrical parameters, so you can measure it in some way. But then, of course, the next question that you have is, as soon as you want to ask these type of questions, right, around longer time scales, around nonlinearities and everything, you need to start putting structure into. You need to start going one scale down and putting structure into your model. That's exactly right. Absolutely.
Yeah. So just to follow up, if I may, on that, Edward. So in this case, where you see this indeed fairly strong nonlinear reshaping, so how much difference is there between the observed repeat lengths, let's say, of this structure and the predicted wavelength?
So in that paper, it's pretty good. In fact, in that paper, so they do measure. And they do actually take into account the nonlinear. They do sort of pretty precise radiological measurements and do take into account this nonlinearity. So they are. They are effectively taken into account in the way that the things are measured without entering too much into details. But at least it's. I think these kind of models are very helpful in terms of also in terms of conceptualizing which different types of parameters act, right? For instance, you can get quite a bit of intuition from this kind of length scale by taking a few simple limits. For instance, if you take, and these show up pretty often, right? If you take if your tube, for instance, would be infinitely rigid. Then it doesn't really care about the sheet, and you go back to your Eulerian buckling, right? So your wavelength would go to infinity. Similarly, if you, and vice versa, right? If you put your elastic sheet to zero, so I think these models are really helpful conceptually, right? To try to start dissecting the kind of scalings and the kind of sort of behaviors that give rise to patterning. But that's exactly sort of my next point. I think. One of the important points, I think, on when these models are helpful, I think these are particularly helpful when these tissues are pretty complex, right? If you think about something like a gut, it's a mix of cells, different layers of muscles, ECM. Making a microscopic model would be pretty intractable because you would have to mix tons of types of tissues. And anyways, a lot of what you observe, a lot of the observables don't really have much to do with these microscopic details, anyways, right? So I think in this kind of concept, in this kind of context, where both your observables and what you can actually measure, your elastic constants, stay at the mesoscopic scale, then this is really this is quite useful because you can get that you can get some quantitative, self-consistent picture for this kind of for these kinds of behaviors. However, I very much agree. I very much agree. The next question is, is there a way that you can go a step below and try to actually understand where these constants come from? Right. That's exactly the next thing I want to go in the next slide. And so in these kind of models where there's not a very clear structure, let's say, where it's a mix of very complex types of matrix polymers and cells, you wouldn't really know what to start with. But if you start with slightly simpler models, which I'm going to show you here, which are essentially epithelial monolayers, one of the cool things is that there's a pretty clear structure that you can see in these tissues and that you can incorporate into your kind of models. So if you think about epithelial tissues, so epithelial tissues are essentially tissues which line, every time you have a surface between the exterior and an organ, you get essentially protective layers of this epithelial tissue. So you can, I mean, so the skin is one, the intestinal wall, the outer wall of the intestine is one, the wall of your lungs, or I mean, essentially most interfaces, you have these layers of tight epithelial cells that serve to make a barrier essentially between the inside and the outside of your bodies. Very often, these tissues, first of all, they're often monolayered, and you can see and you can see here they look pretty structured, right? In particular, they show this. If you look at at a side view, so this would be the outside here of your body, and this would be the inside of your body. You get these. These are not perfectly regular, of course, but you can sort of describe at first a single cell as a prism and a layer as sort of a packing of semi-regular prisms. So this suddenly, and if you think this kind of structure, pretty quickly you might think about forms, right? Because that, I mean, if you think in particular about these the top side here, these look like honeycomb structures. These look very much like ground states of an interfacial phenomena. And that's exactly what I want to go to actually more precisely in this tutorial, is talking about incorporating that level of sort of cellular complexity and seeing how this links back to continuum and how this informs the continuum type models of tissues that I mentioned in the first slides. And again, the reason, so that's just what I said, you know, these tissues have some well-defined structure. They have a polarity. So the up is different than down. They have a clear structure. They're cohesive. Their shape is relatively regular. I mean, this is a lot of information that sounds like it's useful and not too impossible to start putting into a model. Yeah. So I'll explore. Is there any question at this stage, or? No?
Just a naive question. The image you're showing now, is the individual kind of pillars, are those individual cells?
Yeah. Oh, yes, absolutely. Yeah. Sorry, I should say that. So this is, yes, exactly. A pillar is an individual cell. Thanks a lot, actually.
So they're very, very kind of rod-like.
Yeah.
That's very.
I mean, there's going to be a lot of shape. I'm going to show you a lot of different shapes, but the general, that's the general sort of, that's the general gist of it. Yeah.
Yeah, because on the surface, as you say, it looks very much like a pattern that's generated by minimizing surface tension. But I guess the surface tension is very anisotropic, right? You have rod shapes. So.
Yeah, I mean, you're exactly guessing what's going to come in 2 or 3 slides. Yes. Yeah. So I should say this idea. So I mean, this idea of looking at tissues and thinking about forms. This is a really old one. So Darcy Thompson, in his 1917 book, draws extensively on the analogy between embryo and forms. So this is in no way a new idea. But I think one of the cool things in the past 10 years is that it's been possible to revisit the past 10 to 15 years. It's been possible to revisit this analogy in a much more quantitative way. So if you before going into sort of sheets, it's sort of useful to take the simplest case, maybe about a cell doublet, right? So two cells adhere to each other. And if you look at two cells, so this is two cells making some contacts. Again, this is pretty. I mean, you can analyze it quantitatively, and it's pretty close to the kind of shapes that soap bubbles would adopt. And so one thing that people have done in the literature is, well, because this looks like foam, let's and actually because most of the forces are at the surface, so a lot of the cytoskeleton of the contractile cytoskeleton in the systems are in red here, for instance, are at the boundary. You can say, well, this cytoskeleton is giving rise to a surface tension, so let's treat it like a foam, and let's write an effective energy that's essentially a sum of surface tensions. So what you do in this kind of processes, you say is, well, contrary to a foam, in principle, the surface tension at the interface between two cells, this gamma cc, can be quite different to the tension between the cells and the fluid. So you just write an energy which is the area, the cell fluid area times the cell fluid tension plus the area of contact times the surface the surface tension at the contact. And again, and you get, and the advantage is that again you get a single parameter, which is the ratio of your two surface tensions, which is going to specify your equilibrium configuration of your cell doublet. And in fact, this parameter alpha with this ratio of the two tensions, you can read it off in the data pretty easily from contact mechanics, because you know that at the contact these forces have to be balanced, and so from the angle of contact you can extract the ratio of the ratio of this angle, and this is, for instance, from the work of Jean-Léon Maître and Hervé Turlier on mouse compaction. And in particular, what they show here is that the way that cell contacts, the way that cells contact is essentially by decreasing the cell-cell tension. Again, if you think about foams, if you think about two soap bubbles, in two soap bubbles, these things are pretty constrained because this interface is just due to the fusion of two interfaces into one. So this parameter alpha is just half, which means that every angle has to be 120. However, in biology, of course, there's no reason for why this tension has to be the tension at this interface has to be half the tension at this interface. And so this parameter alpha can take any value, and you can get essentially any configuration. You can essentially get any configuration you want. So that's the basic analogy in a two-body problem between cells and foams. You can complexify it. You can, I'm going to go into this. You can complexify it, and this is something, a paper I really like actually from 16 years ago already, that looking at Drosophila, that looked at Drosophila eye. And the eye of Drosophila is usually a very regular structure which consists of these 4 cells, which are organized very much in the type of configuration you would expect from 4 subbubbles. But they could also sort of generate mutants where there was some variable number of cells, and this variable number of cells sort of follows configurations which again are quite close to what you expect just from Plato's law and simple contact mechanics, which again sort of started to validate a bit more validate a bit more quantitatively the idea that you can understand some cellular level or mesoscopic properties of tissues through this kind of analogy with interfacial mechanics. All right. Now the question is, how do you move to a large scale tissue? So as the question was asked, what you can guess is that because in this kind of tissues, actually the cells are super elongated. So this hints to the fact that tensions are going to be very anisotropic. So clearly this tension, the green, I mean, here it really looks like the green tension is going to have to be much lower than the red tension. But in order to simplify, one of the assumptions that was made in the literature is to say, well, maybe as first approximation, maybe I can forget about these 3D aspects. These green tensions are going to be probably quite low. Let's just concentrate on the red part, and let's look at my let's only look at my at the top parts of the apical, the so-called apical side of cells, and let's just forget the three-dimensional aspect of the problem and see this as a problem of two-dimensional as two-dimensional conference tiling. And so there again, I really want to get to 3D, but I will just spend 1 or 2 slides to review what people have done in the past 10 years to look at 2D, just because this is a useful sort of the useful step to start thinking about 3D. But the typical thing that people have done in the past is again get inspired by forms and to say, well, how can I understand these apical configurations? Well, because my cells are truly 2D, this exerts some volumetric constraints. So I'm going to write an energy where I want my apical area of a single cell to be constant. So usually, so you can quadratically expand around a stable state where every cell wants to have the same area A naught. And usually you're going to make this Lagrange multiplier quite large to ensure that cells have a near constant or want to are essentially incompressible in 2D and want to adopt the same apical area. Then you have a second term, which is exactly the one that you would write for a passive form, right? A sum of line tension. So the idea that your contacts here are that there you have a lot of actomyosin cytoskeleton, and that effectively gives rise to an effective line tension. So contribution to the energy that's proportional, that's the sum of all length multiplied by the tension at that length. So again, here this is very much something you would get in forms. However, because this is biology, there's not really a reason that these tensions have to be positive. If you think about, for instance, adhesion forces, you could imagine wetting-like forces where adhesion molecules, instead of tending to shrink, instead of trying to minimize a contact, you could imagine that you have adhesion that tends to provide a wetting force, and that effectively this lambda could be negative, right? You could try locally the energetically favorable thing could be to maximize to increase the size of a given contact, and therefore this is a paper by Farah Defar, in particular the group of Frank Ulisher and Susan Eaton. What you need to do then, if you consider this lambda to be positive, is you need a next order term in your expansion, right? Otherwise, things are going to be unstable. And so the next leading order term that you can write is a term now that's not proportional to length, or not proportional to the perimeters, but proportional to the perimeter squared of your cell. This is what's usually called this active conjunctility here. It's not as easy to interpret physically as the other quantities, which had, let's say, a nice mapping to forms. But you can really see it as the fact that not everything is going to be linear, right? And so you can imagine, you can pretty reasonably write this kind of higher order term to stabilize the system.
Eduard, can I just ask a question?
Yeah.
If there's one thing that confuses me about this image, which probably relates to how this image was taken. If I look at the cells in this image, that the interface does not look like it's actually minimizing the specific energy, right? Because the cells at the interface have nice hexagonal shapes and things like this.
Yeah.
Are they actually minimizing this energy, or is there something about how this image was taken that makes that interface looks funny? So
sorry, you mean interface in 2D or interface in 3D?
I'm looking at the interface in your image. So I'm looking at this, epithelial layer a little bit from the side, and I see the cells at the edge here and they have these nice hexagonal shapes.
So no, I should say this is I don't exactly I think this is SCM. I think this is actually microscopy, and this would be a conference tissue. Sorry, this is not like this in vivo. So you would have, I mean, this is just to see the tissue, but you would not. No. Yeah. So sorry.
So it's not minimizing this.
Yeah, maybe I can comment on that. So it looks like a freeze fracture electron microscopy.
Yeah.
So then you fix it and then you break it.
Yeah.
So that's why it looks so artificial. This is actually you break.
Sorry, I should actually have put the reference for this for the reference of this image. Actually, sorry. Yes, absolutely. No, absolutely. Thanks a lot. Exactly. And so then, but then maybe also pertaining to your case, if you would, if you think about the classical, let's say, foams, you would tend always to hexagonal shapes, and there's quite a few tissues which are even on 2D not perfectly hexagonal. But this is exactly the basic finding from this kind of phase diagram, is that if you're in a regime where your line tension dominates, where your line tension is positive, so this is something in which you have your active conductivity, so your higher order term on the y-axis, and your line tension lambda on the x-axis. And again, I should say this is not my work, right? But if this is positive, you're going to get this hexagonal pattern, so the usual ground state that you're thinking of. But if you start having some linear some negative tension, then it's particularly important to have your active conductivity, and then you start having, instead of a single ground state, you start having soft networks where it's not a unique ground state, but essentially everything is degenerate, and you have a lot of packings with equal energy, which end up with with essentially fluid material which you expect to be able to deform at vanishing energy. And so one way you can see it that's also quite elegant from the group of that was proposed by the group of Lisa Manning, in particular, Dapeng B, is you can see this as a compromise between trying to conserve a given area, which is this term, right? But if I write this term, this is essentially a perimeter. This is essentially minus a perimeter plus a perimeter squared, and so you can see this as a quadratic expansion around the perimeter, around the preferred perimeter, right? So you can see this energy actually as a competition between trying to have a preferred area and trying to have a preferred perimeter. And essentially, what happened here, and which they showed here, essentially, is that what happens is it's really a question of frustration, where cells want to adopt a perimeter, we want to adopt a larger perimeter, but are frustrated by their neighbors, which is why you get this transition from a ground state that's solid to something that's fluid. And so this is again a simple example where to go back now to the continuum kind of to the continuum type of model, where you assume where you look at the mesoscopic level at tissues as elastic. This is a very simple argument where you can get a solid to fluid transition by actually considering some really minimal features of the mesoscopic structure of a given epithelial tissue.
Can I ask Edward to come back to this, the phase diagram, because you can also imagine that if you have this kind of competition, that the outcome is not necessarily a random network, but it could also you could think of getting a modulated phase out of it, right?
Yes, so they have looked. I mean, they have looked, especially if the areas are not all equal. You can imagine quite a few more. I mean, this is the simplest version of this phase diagram, but you're perfectly right that actually, especially in that paper and in the follow-up paper, I think in 2012 and 2010, they look at a number of other more complex lattices that you can get with this. You're absolutely right. This is a simplified picture. Yeah. Yes. Is there any other question before I move to the 3D part of this to the 3D part of this picture? No.
So,
all right.
All attendees, also the ones not in the panel, if you have a question, just unmute yourself and shout out your question.
All right. Again, do please never hesitate to. I mean, you can really interrupt me. Don't. I'll continue, but you can really interrupt me at any point. So so now I want to go back to actually the question that we're asking. I mean, this is in a way, this is nice to describe this 2D aspect, but you can see that in quite a few tissues, clearly there's quite a bit of complexity if you look in 3D, right? But of course, if you look at this kind of prism shape, there's nothing that prevents you from generalizing these kind of 2D energies to a 3D description, right? Where you can still see that there's some degree of regularity in 3D. And so something that we've been interested in as well as other groups is just to generalize this kind of picture to actually write to write these energies now in three dimensions, taking into account the fact that these tissues are polarized, and so therefore that the tensions at the top side, this apical side in red, the lateral side in green, and the basal side in blue, in principle can be anything and can have even different scalings. You can imagine, for instance, as I discussed, that you have both surface and line tensions. So you can get in your, even at the apical side, you can get line tension type of terms, but also surface tension type of terms, and pretty quickly, of course, you need to start being a bit careful because the complexity is going to quite clearly go up. But what you can ask is, can I still dissect some sort of simple features of these organization from similar kind of energetical argument? And the motivation for this is also because if you look at the 3D aspect of these issues, again, they're not all so tall, right? They don't have this rod shape that was pointed out. If you think about, this is a review by Denise Montel in 2008, which I really like actually, and that sort of discussed quite a bit about this. If you take this example, this is the Drosophila folliculocyte. Initially, you get your cells are all sort of so-called cuboidal, where the aspect ratio is essentially close to 1, so everything looks like a square in 3D. And there's this really interesting, if you look a few hours later, there's this really interesting morphological transitions where in specific regions of the oocyte, you end up with this rod-like, so they're called columnar in the literature, so there's really tall cells that start looking like these. But on the other side of the organoid, you get this, it almost looks like a phase separation, right? Where on the other side of the organoid, you get exactly the reverse, where you get pancake-like shapes, cells which are sort of much thinner than they're bigger. And you get a big array of cells. And so one of our motivations actually a few years ago was to try to use this kind of energetical argument to try to see which kind of features could you explain out of this, and in particular, what was the nature of the phase transitions of the type, which kind of bifurcations could you get between this kind of cuboidal shapes with aspect ratios close to 1, and more complex shapes, either very elongated or very flat or very pancake-like. And so again, without going in detail in the phase diagram, one of the really intuitive thing is if you think about, for instance, tensions. If you think about tensions, one really easy thing to get something that has this shape is just to put a lot of tension gamma. If you call gamma A the line tension at the apical side, and if you assume that the cells have to be flat, so if you can find the cells to some to stay on a flat on a flat substrate, if you increase quite a lot your apical your line tension, you're going to go from something which these energies, this type of configurations are going to start costing a lot of energies, right? Because because the parameters are huge, and your energy minima. So here I'm plotting the energy minima as a function of the radius r. So the radius r is a typical radius of a cell in this discussion. You can see that it's not very surprising, right? That if you increase your apical tension, your energy minima shifts from small r to large r. But then, sort of a funny feature that pops up in this kind of models is that even if you assume that the volume of your cell is constant, if you assume your volume of the cell is constant, you can express every geometrical parameter as a function of r, because if you think about the cell in 2D, it's characterized by its height and its radius. But for constant volume, there's a simple scaling relation between.
There's a question from someone in the audience.
Oh, sorry. Go ahead. Of course.
The person can ask it himself, right?
Hi. I hope you can hear me. So
Yes,
I have
we
a
can hear you.
question, which is that in this case, you only consider the tensions, and I wonder what conserves the cell volumes in this case, and whether that choice affects the bifurcations that you're discussing.
Yeah, so that's a really good question. So we did, I mean, in this, when we did this, we did look at sort of so the general picture in this, and the reason generally people assume volume to be constant in this case is that this is thought to be regulated by osmotic forces, and osmotic forces are orders of, I mean, at least 1 or 2 orders of magnitude larger than the tensions we're talking about. So usually osmotic forces are on the order of 10 to the 5 Pascal, whereas this kind of forces are to the order of 10 to the 2, kilopascal, basically. So usually there's a separation of energy scales, which usually means that it's reasonable to first approximation to consider that volume is not, that changes in tensions change the shape of cells without changing their volume, basically, that you can separate volumetric and shape deformations, essentially. That's the basic idea. Actually, we did an expansion. In this paper, we did look at an expansion for finite volumetric compressibility, and as soon as it's not too big, it doesn't change too much this picture.
All right, thank you.
All right. Yeah. So one thing. So again, as I discussed, sort of, if you increase this line tension, you're going to make some cells which are very columnar. It's not very surprising, right? It's making tensions very asymmetric. But one of the funny things that we found is that because different terms scale in a different way, you can pretty generically have either continuous or discontinuous transitions between these types of shapes. Because, for instance, if you think about this kind of of energy landscapes, you can get this, which is proportional essentially to lambda r. So perimeter terms are linear with r, which is exactly this type of shape that you have. But if you think, for instance, about this term, which is the tensions at the basal side, you can imagine it to be negative, and you can and it can be a surface tension, and therefore scale as r squared. So then suddenly, if you sum a perimeter tension at the apical side to a negative surface tension at the basal side, you're going to get some plus r minus r squared, and that's generally going to give rise to non-monotonic. That's generally going to give rise to multiple minimas in your bifurcation diagram. And so, for instance, if you set, for instance, gamma b to a set value, if you set here gamma b to a set value, and in fact here I put gamma a to 0, you can just express your phase diagram as a function of two parameters, of your two remaining parameter, a sum of this and a sum of this, and you can actually get already in a super simple model, relatively sort of rich phase diagram, where your transition, let's say, from a pancake shape to a rod shape, can be continuous in some specific regions of the phase diagram, or can be discontinuous in some regions, with some regions in particular where you could expect sort of phase separation between pancake-like and rod-like cells. And actually, originally, one of the reasons we were working on this is that we were particularly interested in this example, where you get sort of a transition from sort of columnar cells everywhere to half pancake and half rod-like cells, which is exactly what you would get essentially if you start from here, right, and go up in this phase diagram where you have coexistence between different kinds of shapes. Yeah.
Just a quick question. So,
yeah.
If you have coexistence, would you expect that to occur in sort of a well-mixed state, or would you expect them to separate like you saw in that embryo?
Yeah, I mean, so exactly. So I mean, you would expect it to separate, because if you we did play with this a little bit. I mean, clearly, if you try to match cells like this, there's going to be an energy cost at the boundary, right? So what you, I mean, what you can do actually, what you can derive is a Landau-Ginzburg type of picture where you get this energy plus you get a surface tension term that comes from a mismatch between those two configurations, and that's going to give rise to some phase separation of the two, right?
I see. Okay. Yeah. Thanks.
Yeah. Exactly.
Eduardo, can I because that also means that the interface, which you then probably will get, can have a very interesting shape, which is dictated by, you know, the minimal energy way of matching these two very different types of cells, right?
Yeah, absolutely. No, absolutely. I mean, in fact, initially we were, I mean, to be fair, initially we were thinking about the system, and we got quite interested in the system. As often in biology, actually, the system turns out to be quite a bit more different. So it's, I mean, the left side is a bit different from the right side. So it's not actually, it's not really, I mean, it's clearly controlled locally by other factors, which is one of the reasons why we initially, that's exactly what we were interested in, sort of this shape of this interface here, which is probably not the best system to be asking that, but I agree this is a really interesting question. Yes. Yeah.
Eduard, just to keep an eye on the schedule, just keep in mind that we have about 10 minutes left for the tutorial, including questions.
So this is not so bad actually, because I only had a few slides. I only have a few slides left actually. So I might just well, I had 4 or 5, but I'm going to just shorten it to 2. This way it gives time to some questions. The last sort of thing I wanted to talk about is that here so far, this is sort of 3D, but I've still assumed that my tissue was constrained to a flat substrate, right? I haven't allowed for tissue bending, but obviously tissue bending is one of the sort of is a super generic mechanism to give rise to complexity, as I mentioned before, and there's I mean, tons and tons of examples where cells sort of actively regulate their shape in 3D to give rise to bending. But of course, this you get super generically exactly in the same description, right? Because as I said, there's absolutely no reason why your tension on the apical side is the same as your tension on the basal side. In fact, it's not just about tension. They don't have, because there's a combination of line and surface tension. They don't even, you don't even expect it that they have to scale in a that they have to display the same scaling. And so really generically, if you now relax the tissue and you allow it, and you allow cells to, if you now don't impose a 2D, a flat morphology, but you allow cells to minimize their energy in 3D, very generically, your cells are going to adopt, your cells are going to want to adopt this kind of lampshade shapes, right? Which have some, which essentially is a block of spontaneous curvature. And here, if you, I mean, this is really hard not to think about lipid vesicles, right? Because if you, one of the reasons why lipid vesicles is interesting is because you can, because the size of the heads and the tails don't have to be the same, which means that very generically lipids are going to tend to form monolayers with a spontaneous curvature, right? And so in a way, what you can try to explore is really to try to explore this analogy where essentially, even though the origin of your spontaneous curvature is really different, it's some minimization of tension, you might think that the type of building blocks and the type of assembly problem that you're going to give rise to this is going to start looking qualitatively quite a bit like what you get from the physics of membranes. And indeed, that's exactly so. We've looked quite a bit at this. We've looked quite a bit at this. For the same, one of the interesting things is that for the same reason why you can get sort of continuous versus non-continuous versus discontinuous transitions in flat shape geometry, because these don't scale, because the energies of the two sides don't really even have to scale in the same way. They can scale linearly or quadratically with your side length. Again, actually, there's an interesting point where if you increase, for instance, the tension at the apical side, your preferred curvature can vary either continuously or discontinuously. So you can again have continuous or discontinuous transitions in terms of parameter space, which means, for instance, that which if you try to connect it back to continuum mechanics, gives you some interesting behavior where essentially it's the same as some discontinuity in the effective bending rigidity that your in the effective bending rigidity in the bending rigidity of your monolayer. And in fact, this is something that has been explored as well by other groups. I really like in particular this work from Primož Zihel in the past last year, where they explored really quite quantitatively this kind of analogy between vesicles and cells. So there's this classical result where if you have some lipids that have a spontaneous curvature, which can be positive or negative, and you enclose a set volume, you get quite a rich shape of you get quite a rich type of shapes. You can get some you can get this so-called so I mean the basic physics is that if the volume which is enclosed by your lipid vesicle is very large, of course you have to be spherical. But as soon as your reduced volume of your vesicle is less than 1, you start having some flexibility to the membrane to deform, and that's going to cooperate with your spontaneous curvature to give rise to relatively to quite non-trivial shape in 3D. And in fact, if you now do the same type of diagrams where instead of your spontaneous curvature, you look at the ratios of your tensions on both sides, you get in these kind of vertex models relatively similar. I mean, qualitatively similar phases. Of course, the different. I mean, there is again slightly different physics and slightly different non-linearities. So the phases are not the phases are not the same. But but you can really make quite a strong analogy between between this kind of active foam models of tissues and sort of coarse grain, let's say coarse grain them in models that start looking very much like models of vesicles. And actually, I mean, I had a few things on this actually, but actually it's probably a good time to stop if people want to ask questions.
All right, thanks, Eduard. We do have a few minutes left for some general questions. So please, if you have a question, just unmute yourself and shout out.
Yeah, Eduard, one thing I'm interested in is to hear, somehow it seems to be in the background you are assuming that basically your 2D layers of cells will always remain coherent. Yeah. Of course, in nature, you can think a rupture may occur, yeah. Cells may actually be expelled from these layers. So where is that hidden in this formalism in a way?
Yeah, so absolutely. So this is a very interesting point. So we are, I mean, that's absolutely true. So if you think about all these models, essentially, the key assumptions is that you're expecting them to be confluent, basically. So you're not allowing any holes. So that's you're making a very strong assumption. In particular, it can give rise to some slightly bizarre things. For instance, if you think about things in terms of liquid versus rigid, you can put your adhesion to 0. Putting your adhesion to 0 is like increasing your line tension because that's increasing wetting, and that essentially tends to rigidify tissues, which of course is a bit weird because in the limit of 0 adhesion, then there's no reason for the constraint of 0 volume. I mean, we've started. I mean, I can share. I mean, if you're interested, I can share. I can just share just a picture from a slightly different presentation, just to stay in the informal spirit of this. We've been thinking exactly about this in terms of if you can sort of go from a model of foams to a model of let's say granular media somehow by tuning adhesion, right? If you think about, let's say, floppy structures, so if you think about 4 cells which are absolutely non-adhesive, there's going to be a lot of fluid. I mean, there's going to be a lot of fluid around. And from a rigidity perspective, this structure is floppy, right? You can deform it with 0 adhesion. But if you change this alpha parameter, so if you essentially reduce the tensions between the 2 cells, initially your cell-cell contacts are going to expand. You're going to get exactly the same picture as a two-body problem. So the fact that it's a four-cell doublet doesn't matter. You get exactly the physics of the two-body problem. But at some point, when you expand, you're going to start getting a triple point. Your contacts are going to you start actually making vertices, actually removing your fluid, and then suddenly this kind of physics sort of works. But there's a crossover, right? Where there's a crossover of adhesion where this kind of rupture. This is exactly this is exactly the kind of this is things we're super interested in actually, and things that OJ Compass actually has also recently put something on bioarchive to try to look at the crossover between this kind of this sort of confluent tilings and conference and non-conferent tilings. But that's there's also some work on Manu Prakash on rupturing these kind of models. But that's extremely topical. That's absolutely I completely agree. That's really interesting.
I actually have a question concerning the network topology. So, I mean, if you think of a work by Xavier Trepard on epithelial domes, or for example, your preprint on these intestinal organoids, you see that already a mean field approach is actually quite successful at describing the general mechanistic ideas. Do you think that this exact substructure which you have in these vertex models is necessary, or do you think this is a bit overkill in the end?
Yeah, I mean, that's a really good question. I mean, I think it really comes to where you are. I mean, I think it really comes to where you are in this phase diagram, right? If you're deep in the hexagonal network and you put a bit of noise, probably it's fine, right? Because essentially everything coarse grains into everything coarse. I mean, you get some. It's rigid. You get some elastic constant, and then you can have some noise around that, but it probably doesn't matter, right? But let's say if you're close to this transition, then suddenly your amount of right, if you can reorganize quite quickly, then suddenly your noise starts mattering, because you really get sort of again you get sort of fluid to solid transitions in your sort of coarse grain properties. So then suddenly it starts mattering quite a bit, right? So I think it might. I think that's my general view, right? Whereas if you're deep in some rigid phase, yes, it probably the detail of the substructure doesn't really matter. That probably doesn't matter, but there's probably quite a few systems which are close to some rigid solid transitions, solid fluid transition, and there the actual structure starts mattering quite a bit, right?
Okay, thank you.
Yeah. The other thing which I didn't mention is that which I didn't have time to mention, which is actually work by from a paper by Guillaume Salbreux, is that you can actually you can systematically coarsen this kind of vertex models and get your sort of continuum parameters out of the vertex model, right? Which is again quite useful, because then you really do have some link between between observable tissue structure, let's say, and continuum parameters. But there again, this is noise. I mean, this is again mean field. You're absolutely right.
All right. So in view of the time, Edward, and we should probably take a small break here. So thanks so much for the very broad overview and the super nice discussion. I propose that we take just a 5-minute break so everyone can grab a refreshment or run to the restroom, and we'll continue at 20 to 5.
Okay, cool. All right. Stop sharing for a second.
So welcome back everyone for the second half of the meeting. So we're now going into a round where we're going to do 2 research talks. The first one is going to be by Eduard again. So for those who tuned in later, Eduard is from the IST in Vienna. And Eduard, just go ahead whenever you're ready.
Yeah, I mean, thanks. So I'll actually continue on a bit on this description of 3D vertex models. I mean, so what I've described, like in the tutorial, is that I think these vertex models are quite. What they're good about is that they're quite a simple description that takes parameters which are in principle measurable, these sort of tensions, and make some simple predictions out of the on the mechanical state and the mechanical and the resulting shape of tissues. But of course, if you look in biological tissues, it's not just about mechanics, right? It is not usually everything I've shown you before. There was a single cell type. It was purely tension, etc. But clearly that's not the case, right? There's different cell types. There's some reaction diffusions. There's some geometrical constraints from the exterior. There's quite a lot more than this. What goes on, and one of the things that interests us the most is essentially in the lab is to use these vertex models as a base point, because as a sort of a mechanical model that we sort of start to understand, and to take it as a basis to start adding little by little a bit of that complexity, of that biochemical complexity, that complexity around cell fate, et cetera, et cetera. And so this is several things that we've been working on in the lab, thinking about how to add to these vertex models, either cellular fate or biochemical signaling to give rise to waves, etc. But actually, in the sake of time today, I'll only talk about the second part, which is to generalize these kind of vertex models to multiple tissue types, to try to understand how organoids get their how intestinal organoids get their shapes. And I should say straight away, this was a really fun collaboration with the lab of Prisca Liberali, who's the expert on this on organoid biology. And in particular, all of the experiments I'm going to show have been done by a postdoc in the lab, Chutan Yang, and all of the modeling of all of the theory I'm going to show is done by a great postdoc in my lab, Sholei Shui, that joined 2 years ago. So what's interesting about these intestinal organoids is that they're a really simple system which you can culture. So essentially a monolayer, a closed monolayer. So it's a spherical monolayer that first breaks symmetry in cell fate. So essentially you start from a monolayer that's homogeneous, where every cell is the same. You break your symmetry where there's some stem cells that emerge on this side. And suddenly and at the end, what you get is 2 domains, one domain of stem cells here and one domain of differentiated cell here that looks very much in many ways like the actual wall of the intestine. And it seems like the symmetry breaking here in fate happens prior to the symmetry breaking in morphogenesis. So one of the questions we had is, it sounds like the stem cells, both in vivo and in vitro, are always in this kind of neck here. And that's a question of what exactly in cellular fate, what in these stem cells makes it so that it coordinates their shapes, the shape and the final morphology of the epithelium. And so this is an actual morphological sequence where you go from something flat, you get your stem cells in green here, and at the end you get these shape deformations where your stem cells are in the neck at the bottom here. And this is really the question that we wanted to ask, which is both, I think, interesting because it's a way to study a complex organ in vitro, but it's also a way in which you can manipulate a simple but yet a simple one-layered epithelium, which still has quite some level of complexity. So the first movie that they did is to actually the first thing they did is to actually image these organoids. And one of the very interesting things that you saw is if you look at these organoids, the way they break morphological symmetry, you can see something that looks very clearly like apical tension, right? Here, these cells, the apical side here is very curved. The apical side is very curved, and the basal side here is very relaxed. It's clear that these cells have this sort of lampshade type of cell, which I discussed. So which really makes it look like apical constriction is going to play a role, which is actually something that has been observed in vivo as well, has been proposed in vivo in intestinal crypt. However, you then also find something which was funny. If you look at this movie now, you get again initially something which is very cool. This is just a 2D cut, and this is a maximal intensity projection, but this is the same movie. And you can, I'll run the movie once. You can see that the movie suddenly this deforms, and here you get again a crypt here at the very end. But something that she noticed here is it doesn't exactly just look like apical constriction. If you track the volume of the fluid in the center, which is this orange thing, you see that the fluid, the volume in the center decreases by quite a lot. Here you can see. I hope you can see here the volume inside. Sort of, if you calculate the volume here in 3D, this decreases by quite a bit, right? This decreases by 60%. And this is pretty interesting because if you then maybe it's not so much about, maybe it's not just about apical constriction. Maybe I should think about it more as a deflating football, right? Because again, in the buckling picture I told you before, if I think about a football, right, and I deflate it, of course I'm going to make some folds in an easier way, right? And if I change my surface to volume ratio in these organoids, that's also a pretty simple route through which you could get this kind of morphogenesis. So it really seems like there's some myosin actomyosin dependent apical constriction, but there's a clearly dramatic relocation of fluid from the lumen to cells. And actually, I'm not going to go into detail, but when they looked, it's sort of interesting where it's not that the fluid exits the epithelium. If you look at the total volume of fluid plus cells, this is pretty constant. So it's really a relocation where the fluid leaves the volume and enters the surface, which really increases massively your surface to volume incompatibility, right? So that really sort of is gonna favor some buckling type behaviors. And so for this, we thought, okay, we need some biophysical to turn to the biophysical models to try to understand the balance between these different forces. And again, if you mix now these two things, if you mix apical constriction and volume to lumen, volume to surface fluid relocation, again, it's to continue on the tutorial, it's really hard not to think about lipid vesicles, right? Because if you think about, for instance, classical work from Julisha and Lipovsky, if you look at the configuration now of vesicles which have a domain of spontaneous curvature, so here in red you have a domain which has a spontaneous curvature. If your fluid is very large, of course you're going to get something spherical. But if you start deflating a bit the center, you're going to get a budding transition where it's energetically favorable from a curvature perspective to allow this domain to adopt this small sort of budding phenomena. So just by playing so in this kind of super simplified in this sort of simple systems, already you get some interesting interplay between some spontaneous curvature and lumen volume to surface ratio, which is again exactly the two components that Chutan was seeing in her movie, right? So what we did is again to take actually to take the tissue analogy of this, we wrote down a 3D vertex model which was enclosing a volume of a set volume, and we allowed the stem cells, the stem cell domain, to have properties which are in principle, which can be, I mean, in principle they can have any properties, and of course the stem cells can have any mechanical properties which are different from their differentiated cells. And we wanted to ask, which kind of morphological, do you get similar morphological transition, and can this actually explain the data? So what Shirley did is to ask which kind of behaviors you had with this, and how could you give rise to this kind of budding phenotype you saw in the data. And of course, there's a number of parameters, but again, if you what Shirley could show is that you can actually reduce the parameter the parameter space to only very few, and there's only if you constrain everything, you can see actually there's only really 3 classes of mechanisms. Of theoretical mechanisms which can give rise to a bodied shape. The first one, which is essentially sort of bending, so out of plane moments, and it's the idea that, well, maybe your stem cells have spontaneous curvature, have apical tension, and that's exactly what we've seen before, right? So you put apical tension here that constricts, and so you tend to bud. But if you think about it, not in terms of out-of-plane moments, but just just in terms of in-plane rigidity, you could imagine, for instance, that your stem cells are much softer than your surroundings. And if you imagine now a balloon which is pressurized and where one domain is much softer, the softer domain is going to dilate, right? It's going to be dilated because the pressure is constant inside those balloons. So you could also imagine budding with your sort of stem cells which are much softer. So this is essentially sort of curvature term, and this is some in-plane term in your energy. And then the last thing you can do, which I'm not going to talk about too much, you could imagine a boundary term. You could imagine that somehow the stem cells and the differential cells don't like each other too much, and so you have a boundary term in your energy that penalizes your boundary. But the advantage is that all of those, if you actually now look at the morphometrics of your stem cells, each of them are going to give rise to different scaling laws. Yes, in terms of radius of curvature, all of them are very similar. But if you look, for instance, at the height ratio, these are completely opposite. So if you look at the height ratio between stem cells and differentiated cells, in this picture, because you put a lot of tension on your apical side, your stem cells are becoming thicker and thicker. They're becoming columnar, more like rods, because you're putting a lot of apical tension on the side. Whereas if your crypt is softer, it's going to be the reverse, right? The reason why your bud is you're softer, and actually your thickness is going to decrease in stem cells compared to your differentiated cells. Whereas if you have a boundary term, basically to leading order, your thickness is not going to matter because both of them have the same in-plane stiffness. So we reasoned by looking at this, by looking at these very simple observable scalings in the data, we could distinguish broad classes of mechanism from a theoretical side. So that's exactly what we did. What Shirley and Chutan did is to segment these organisms, these organoids, and to look during budding to what happens. And what is very clear qualitatively is that when a crypt here buds out, it was quite clear that the thickness was getting much thicker. So actually, if you look at the thickness ratio, at the thickness ratio between stem cells and differentiated cells, in time, in every organoid it increases as the ratio of radius of curvature decreases during budding. Of course, the problem is that every organoid has a different timing, right? They're slightly different. So of course, you can assume some temporal evolution of your parameters, but and you can fit the data and the lines as a fit by assuming a linear evolution of your tensions. But it's really unsatisfactory from a theoretical side, right? Because essentially you can fit anything, right? It's completely it's a super weak it's a super weak thing because everything depends on your temporal parameterization of your data. However, what Shirley realized is that what if you could eliminate time by now plotting one observable as a function of the other? What if if I try to plot theoretically my thickness ratio as a function of my radius of curvature ratio? And what was cool is that Shirley could actually derive analytical scalings in which you can derive super simple scaling forms. For instance, if you assume that it's this scenario 1, spontaneous curvature, you can derive super simple scaling between your ratios of curvatures and your ratios of thickness, which depends only up to a single scaling parameter. And in fact, I'm not going into the detail, but this scaling parameter you can constrain independently through other metrics. So if you do that, if you now you have a very simple scaling law predicted by the data, and with up to a single rescaling parameter. And in fact, if you take all of this sort of complexity with up to a single parameter, you can rescale your radius ratio as a function of your predicted functional form for your thickness ratio, and you seem to collapse quite well your complexity just by taking into account, in particular, the fact here that different organoids had different aspect ratios. So this was a slightly stronger test of the model, by essentially plotting. Predicting in 3D vertex models scaling laws between actual observables. You can do the reverse route, of course. You can actually test it a bit more quantitatively in the data. What we did first is to now really do a phase diagram of organoid morphology. And again, in analogy to lipid vesicles, what we did is one thing that matters is the apical tension of the crypt of the stem cells. So this is essentially what's going to specify your spontaneous curvature, and you can check that in time. In fact, if you look at myosin staining at the apical side, it does increase linearly, which is very much what we had fitted from the model. But it seems to be the case if you look at your myosin in time, which is a good check. But your other parameter, right, the other player which I talked about, is this normalized volume. The fact that you get relocation of fluid from the lumen to the cells. That actually is also later in time, in developmental time. If you look later in developmental time, you get a pretty strong decay. So if we looked actually at the data in terms of actomizing forces and osmotic forces, we could sort of sketch this kind of developmental trajectory, developmental trajectory in parameter space. But we thought, okay, can you actually understand it a bit more quantitatively again? And one of the fun predictions that emerged in this vertex model is if I start, for instance, if I start here, right, and I increase my crypt apical tension, or if I increase my crypt apical tension, I go here, my crypt is budded, my crypt in red has budded, but now if I increase my volume back, I go back to something spherical. This is exactly lipid vesicle physics. This is exactly what you expect. Something which was a bit funny, however, is that there was a phase transition where if you go and you increase your apical tension up to above a critical value, you can increase your volume essentially to infinity, actually, and your crypt never opens up again. And this is not something you actually expect. Usually for lipid vesicles, things always open up. But actually, this is very general for vertex models. And the reason for this is that when you put actomycin on your apical side, you increase your spontaneous curvature, but you also increase in-plane rigidity because you also make your crypt stiffer in planes in plane. And so because of that, when you re-increase your lumen volume, not only your crypts wants to stay curved, but they're also stiffer. So then suddenly it's the blue differentiated cells that take up all of the deformations. You can actually test that in the data, but we thought, okay, actually you can test it. If that's true, we can test it in the data. And what Yu-Tan did is to take this kind of early organoid, which are slightly budded, which has like here developmental, which is in this developmental time, and she could put a pipette, and she could actually inflate it. So using pipettes as a rheometer. And again, because this is fluid, so it means that the pressure has to be sensed the same way by the stem cell and differentiated cells. And what you can see is if you do that, your stem cells dilate quite a bit, and you go back to something much more spherical, which is what you expect here. However, if you take a late organoid now, and you do exactly the same manipulation, so this is a late organoid where your actomycin is quite high and your crypt is sort of quite budded, you can do exactly the same experiment. But actually now all of your deformation is borne by your differentiated cells. So all of your deformation here got deformed, and the crypt didn't move in any way, which is exactly what you expect again quantitatively if you passed this transition in morphological space in your 3D vertex model. And I just want to, I'm actually going to end up with this just to leave space for a few questions. The very brief thing I want to say is that in principle, you can make this a lot more quantitative again because pressure has to be equal. I mean, pressure, it's fluid pressure, so it's equal to everywhere. So you can use this as a rheometer to really probe quantitatively differential stem cell differentiated cell mechanics, right? And in fact, again, what Cholet could do is it could predict now, say, for the short time frame, the mechanical parameters are not changing. It's only the volume that I'm changing. But then you can predict, again, scaling laws between radius of curvature and volume, or even between radius of curvatures and thickness. And again, you can derive quite a few things analytically. And again, what was quite nice is if you compare the different morphological ratios as a function, for instance, of the volume that you've injected in the pipette, you get a pretty good agreement with the scaling laws that you derive through the vertex model. And in particular, one of the key things, if you look at the radius of curvature, at the ratios of radius of curvature, for the early organoid, this increases back, so you go back to 1, which goes back, which means that your organoid went back to something more spherical. Whereas if you go for late organoids, your differentiated cells in blue took all of the deformations. So actually, your radius of curvature gets more and more different and goes more away with 1, right? And this sort of inversion of the monotony, the inversion of the slope of this is exactly what you expect, sort of above and below, as soon as your organoids sort of passed essentially this phase transition. And that's basically, I mean, I mean, there's a few more quantitative aspects to it, but actually I'm going to stop just to leave a few questions. I just want to acknowledge Yu-Tan and Priska because it's been really a fun collaboration, and Cholet Xue that did all the work for this project. Thank you very much for your attention.
All right, thanks so much, Eduard, for a wonderful talk. So we have some time for questions. So all attendees, please write your questions in the chat, and I'll first give the opportunity to the panelists to ask their questions. So maybe I'll just get started here. So I was very intrigued by this collapse, Eduard, from the different organoid data. But there was one thing in there that just went a little bit too quickly for me. So there was this parameter that you need to collapse the different organoid data. And this, from what I understood, this parameter is different for each organoid. Yeah. Because it somehow depends on an aspect ratio of something. Yeah. Could you say something about what it actually depends on, and whether it will actually change, whether you expect it not to change over time, so that it's actually constant for each organoid, so that you can use it in this collapse? Yeah. So that's a really good question. So these parameters, if you look at this rescale parameter, this is a product of three terms. These two, they're purely geometric. So these actually we measure. They're actually not a collapse parameter. We actually measure them. So this is the fraction of stem cells. So this is the fraction of the domain, the size, the relative size of the two domains. So this is how much, this is the length, the red length divided by the total of the length. And K is the aspect ratio. So it's essentially the thickness of the monolayer initially divided by the overall by the overall radius of the organoid. So these are really geometrical parameters which actually are not fitted. These are, and how much does it actually vary from organoid to organoid? Is it a bit? So there's 2 or 3. A factor 2 or 3, not massively. Not massively, but it does a bit actually. And actually, quite a lot of the variability comes from these differences in aspect ratio. Actually, this is the parameter that we fit upon, that we rescale against, and essentially it's what's the rest length, the rest volume, because what you assume essentially here is what's the volume. What you don't know right in the data is what's the volume at which everything is at equilibrium, right? What's the volume at which initially the monolayer is at rest. And so effectively, what this V naught tells you is how far away from that volume you are. Essentially, so here, when you start from 2, essentially it means that V naught equals 2, right? It means that you start from an inflating, that the organoid start from an inflated configuration where the epithelium is on the stretch. And so the reason why I say we do independently constrain it is that when you now fit these things, when you now fit these things, there's also V0, there's also this V naught that shows up, and the value of V naught that you get when fitting the pipette aspiration are consistent with the V naught that you get in the morphological things. So it's not something that we can quantitatively get, but at least it's not a complete sort of non-physical variety. It says that there are some constraints between the different assays, let's say. All right, fantastic. Thanks so much. Any other questions from around the room?
So maybe you can summarize. So what's now mechanically different in the red part?
Yeah, so I should say so essentially here we can fit. Not sure if I have it here. So here essentially we can fit. The only thing that we assume by fitting is that the apical tension, so the actomyosin in the inside of the stem cells is higher actually. And I don't think I have a staining in there, but that's very much what you see. So if you stain here, this is actually the amount of myosin that you have in the inside of stem cells compared to either to the villus or to the outside cells of the cell cells, and you do see sort of massive relocation of actomyosin in the inside surface of the stem cells compared to the outside, and also compared to the differentiated cells. And
you think that that's just a transcriptional difference? They just express more myosin?
So it's really, I think we think that it's a good question. We don't exactly know. We think it's more regulation because it seems like it's also, in fact, it seems that they're basal. So the outside part goes down. So we think it's more relocation. It's not that the total amount of magnesium changes so much. It's more that the localization is affected by fate.
So and is it in the stem cells and also the punnet cells next to it?
Yeah, so that's a really good. So that's a yeah. But so indeed, so you're right. So the scripts are made of two cell types. So what Chutan did for this is to make organoids which are enriched either in stem cells or in Paneth cells. And what she finds is that the spontaneous curvature in the myosin is highest in the stem cell enriched organoids. So it seems like the Paneth cells do contribute a bit, but the stem cells, really the LGO5, let's say true stem cells, seem to have the strongest contribution to spontaneous curvature, at least when she was she was playing with different treatments to sort of enrich for different cell types, and that's what she that's what she found. But it's not a 0-1 result, but it does seem like the LGO5 stem cells are the dominant contributors.
Yeah, so it's very interesting. So if you would grow a normal spheroid, and then you could locally with light stimulate contractility in one part of the spheroid, you would get the same shapes.
Yeah, that's a really, yeah, in principle, I mean, that's a really interesting point. I mean, I know that in Drosophila, this has been looked at where people have tried to optogenetically make constriction, right? I know that in Drosophila, people have done this and it seems to work. Yeah, I mean, it's really a cool experiment. But I agree, in principle, it's cool. I mean, yeah, that's a cool experiment. Yeah.
Yeah. So blebistatin is also light sensitive. So if you illuminate it, it's inactivated. So if you illuminate the whole thing except for one spot, then you will locally increase contractility.
That's a cool. Yeah, that's a cool. Yeah, that's a cool experiment. I mean, we did. I mean, so Chutan did sort of use overall blebistatin just to and it does what you expect, which is to go back down. Let's say you go back to spherical, but it's really especially that's a cool. Yeah, that's a really cool idea.
Yeah, it's very interesting. This explanation for this sort of crypt formation. So it's very. But also normally in development, of course, you have multiple crypts, right? So does it work for that? Probably yes, when you have local more contractility, you just get the butt there, right? That's the idea.
Yeah. So I don't know enough. I mean, I know that. Initially, there's like a 2D labyrinth, right? In development, there's like a 2D labyrinth of LGO5 cells, and then this organized into spots, right? But I don't know how much I don't know actually what comes first. Is it first morphology or is it first stem cell restriction? Actually, I don't know if people have. I don't know actually. This is a good. In organoids, it seems like fate comes before shape, let's say, but I don't know if this is. Yeah, I don't know actually about that. If how exactly this translates to in vivo. This is a good question also.
I have a very general question. You know, it's not a particularly refined question, and maybe it would have been better asked at the end of the tutorial. But this class of vertex models you're solving, it's clearly, you know, beautiful how you can capture, you know, some of these non-trivial morphologies, right, and the dynamic. But I guess in terms of what goes into the model and how you solve it, it's really just a mechanical equilibrium that you're solving. Right? So nothing, am I correct in understanding that in the physical problem you're solving, there's nothing inherently out of equilibrium? So of course, implemented, of course, by things like, you know, actin, myosin, you know, which is far from equilibrium. But I'm just wondering if it's theoretically possible to construct a material that would do this in an equilibrium system. Yeah.
I mean, yeah. So first of all, yes, you're absolutely right. So we write essentially work functions. I mean, things that I mean, effectively the coefficients arise from an equilibrium. You're absolutely right that all we're doing here is minimizing effective energies. That's absolutely true. I think one thing I should mention here, which I think is one of the reasons, is that one of the things that obviously wouldn't be covered by this is all of the dynamics of it, because the dissipation, I mean, the whole dynamics of short-term dissipation clearly would or sort of, if you look at local fluctuations of your shape, this clearly would be this clearly would be a much more truly non-equilibrium phenomena. Here's one important thing, and I think that's one rationale that people use, is that very often these are timescales of hours and days, right? And so whereas the timescale of dissipation, I mean, the timescale of dissipation for actomizing or something like this would be minutes to tens of minutes, right? So here, that's why I think, because it's hours to days, I think it's reasonable to assume that essentially you have at every, this is quasi-static, right? At every point, I mean, your cells are super slowly maturing, and your parameters are evolving slow enough that you pass through a series of equilibrium points, right? But I agree that if things would go faster, for instance, there you would get much more sort of non-equilibrium dynamic, much more sort of complex non-equilibrium dynamics, I guess.
I see. So yeah, even the very rich phase diagrams you were showing earlier, they can all be realized just with equilibrium mechanics in principle, I guess.
Yeah, exactly, absolutely. Yeah.
Thank you.
Yeah.
All right. I want to thank Eduard for the wonderful talk and discussion. We really need to switch over to our last talk of today right now. So Sophie, I think you've joined. Welcome. Please
Hi.
Go ahead.
Thanks for having me.
Yeah. So the last talk of today is going to be by Sophie Dumont. I just want to quickly introduce her. She did her PhD at Berkeley, the Bustamante lab. Then went on to Harvard as a junior fellow. And after that, she moved to UCSF, started her own lab as an assistant professor. Now she's an associate professor. Her lab is very broadly interested in how the cell integrates biochemical and mechanical processes, especially to regulate the chromosome segregation machinery. And this is also what her talk is going to be about the spindle and how it can be mechanically robust with dynamic parts. So thanks so much for joining, Sophie. We're looking forward to your talk.
Yeah, thanks for having me. Thanks for the invitation. I'm excited to be here. I love traveling, and I have yet in my life to go to the Netherlands, which I really don't understand, but at least I can virtually come now. So I'm excited to tell you about a new project in the lab. And before I do so, to build it up, I'll tell you about, very briefly, some published work. So here's the big picture question that I've been excited for a long time, and that my lab is excited about. It's the question of emergent mechanics across scales in biology. So ultimately, the mechanics of molecules will give rise to those of cellular structures in cells, and those of cells will give rise to those of tissues and organisms. And the question is how does that happen? And the mechanics of a building, which is not consuming energy, that relates to the previous discussion, are very predictable. And in San Francisco, we have fancy things like buildings that are earthquake proof and such. In biological structures, the structures that biology builds consume energy. They're dynamic, they're self-organized, and what mechanics emerge are much harder to predict. However, the mechanics that emerge can do a lot of cool things that this building here cannot do, like biological structures can self-repair, for example, and things like size emerge out of nowhere. And, so that's the big picture question that we're excited about. And if that's a big picture question you're excited about, then cell division is a great playground to ask this question. Because at cell division, every time a cell divides, self-organization is key to build the spindle, to build it from scratch every time. And the spindle's main function is indeed to generate mechanical force. And as such, it needs to have very specific mechanical properties. So as you'll see in this movie, and this is a movie of a mammalian cell dividing, the spindle is dynamic. It needs to be dynamic for chromosomes to move within it. It's flexible, but it also needs to be robust, and it needs to be able to generate force. And just in terms of complexity here, the spindle in mammalian cells has got just about the same amount of parts as a Boeing 747 airplane. And answering this question of how does the mechanics of the spindle emerge, and how can the spindle be so robust given its dynamic parts, has been challenging, in part because it's hard to physically probe large cellular machines inside cells. We have limited tools to do that. And it's also hard to reconstitute many of them, like the mammalian spindle, in vitro. So the big picture question I want to ask today, and by no means answer, although I'll provide some baby answers, is the following. How do the mammalian spindle's robust mechanics and function emerge from its dynamic parts? And to get more specific by what I mean by dynamic parts, I mean two things. I mean that they're parts that grow and shrink, namely the microtubules here. In each of these thick yellow lines, there are about 20 microtubules, and these constantly grow and shrink through dynamic instability. And a given microtubule might live for a few seconds to a maximum of a few minutes. Yet the spindle lives for an hour. So how does a spindle maintain its structure with parts that grow and shrink on seconds and minute timescales? And then these red things here are molecular motors that move microtubules, and they too bind and unbind with seconds timescales typically, or maximum minute timescales. So how can the spindle be robust and maintain its structure and be mechanically strong and yet use all these dynamic parts? And both of these concepts are clearly essential for spindle function. So if that's a question you're excited about, and if you want to understand how the spindle is so rigid, a dream experiment you might want to do is to actually go inside a cell and tug on a spindle, which our lab spent a lot of time developing in mammalian cells, and which we've recently gotten to work. And this is based on classic work from Bruce Nicholas 50 years ago in these strange cells called grasshoppers, spermatocytes, in which this was much easier. But basically, we come in with a glass needle, and you pull on the spindle, and you can look at the deformation map, and you can learn, for example, if you exert short-lived forces, you can learn what kind of connections hold the spindle together in short space and time. And if you exert a pull over many minutes, over long time scales, you can learn how the spindle remodels itself in space and time under force. And this work was spearheaded by Pooja and Alex, who are two fantastic biophysics students in the lab. And here I'll just tell you basically what we found without going into the details, just to set up the main piece of work. We found two things. So if you exert short pulls, we found, as you will see in this movie, that microtubule bundles appear free to pivot around the spindle pool, which is here. However, they do not appear free to pivot around chromosomes. Namely, if you look at the cartoon here, this bundle, which is now gray, appears to be forced to go straight in the center of the spindle, and it is not free to pivot. What does this tell us? That tells us that it seems, and we've shown this with data, I'm not showing you, that the spindle is reinforced in its center, which we're excited about because that's exactly where the spindle is most dynamic, because this is where chromosomes are and this is where microtubules are growing and shrinking. So it seems that the spindle, to maintain its structure, might be using this design principle of just reinforcing its structure where it's most dynamic. And of course, this microtubule bundle here refusing to pivot also ensures that the two sister bundles point to two different spindle poles, thereby promoting accurate segregation by forcing the two sister chromatids here to be hooked up to different spindle poles and therefore to go to two different daughter cells. What kinds of things can we learn if we pull for many minutes? You can see how basically the force that you're putting into the system gets dissipated, how the synergy gets dissipated. And what you see in this movie here is that if we pull on the bundle of microtubules, it gets longer and longer, which is actually deeply connected to some classic work by Marilyn Doctorum some 20 plus years ago. So if you pull on this bundle of microtubules, it gets longer. And then we wanted to know, of course, how does it know to get longer under force? You could imagine that microtubules within the bundle would be sliding. That does not appear to be true because if you photomark a population of tubulin, this white mark here, you can see that this photomark doesn't get wider, which you would have expected if they were sliding. And you can instead show that the distance between the photomark and the plusins of microtubules neochromosomes here, right, this red bar, gets longer over time. And normally this distance would be getting long and short and long and short, but here it just continuously gets longer. It stops depolymerizing. So microtubules stop depolymerizing by their plus ends. And they also stop depolymerizing at their minus ends. And normally, this is just a funny fact about spindles, microtubules normally depolymerize at their minus ends into spindles. So somehow force has turned off the option for microtubules to depolymerize at their minus ends and at their plus ends. And we don't know how this happens. But we're excited about this because it means that basically force locally applied in the spindle gets locally dissipated by this spindle getting longer rather than by force getting transmitted everywhere. And this has some clear implications for possibilities of force transmission in space-time over the spindle it seems that forces are fairly locally isolated. Right? And this might allow, again, answering this original question, the spindle to maintain its global structure by very locally dissipating force. So that's kind of the summary that sets up the stage, right? So if you're thinking about what principles allow the spindle to be dynamic yet robust, one might be that it's reinforcing its center where it is most dynamic, and the other might be that it's locally dissipating force by, in this case, for example, allowing microtubule bundles to grow under force instead of force being propagated elsewhere. So where am I going with this? I'm going to the following place. We wanted to know what makes the spindle so robust. Like what else is helping keep the spindle structure so strong? And one thing that people who've studied the spindle for decades have figured out is that there are very often motors that appear to oppose themselves in the spindle. And so here there are blue motors called dynein and there are red motors called kinesin 5, but there are other pairs of motors that oppose each other. And in many, many species across evolution, there appears to be this concept of motors that are just consuming energy to oppose each other. So why are they doing this? What's their role? And in the spindle in particular, these are movies not from our lab, but from in vitro system. And this is related to work that Lucas has done. Kinesin 5, this pink motor here, exerts extensile stress in the spindle, meaning that it likes, what it does is to expand networks of microtubules by walking along antiparallel microtubules and pushing them apart. And in contrast, there's contractile force powered by the motor dynein, which is this blue motor here. And this motor dynein is carrying in the spindle other microtubule minus ends as cargos. And dynein, as a rule, is walking to minus ends. What does it do? In the spindle, it carries minus ends to other minus ends. Therefore, it exerts a contractile force, and it helps build asters of microtubules. So in vitro, if you have microtubules in your system and dynein, what you get is asters of microtubules. So in the spindle, there are extensile and contractile forces that oppose each other. And if you look at a wild-type spindle where nothing is removed, then the spindle at metaphase is just at steady state, like in this movie here, keeps the same shape and size. If you remove the contractile force, which we do here by depleting this protein pneuma, you can see the spindle never reaches a steady state. All it reaches is this turbulent network, a turbulent mess, basically, of microtubules that are just hitting the cell cortex all the time. That's if you remove the contractile force. If you remove the extensile force by inhibiting this kinesin 5 motor with the drug, if you just add this drug on a spindle, the spindle collapses in many cell types to a monopole. And that's because forces that kick microtubules outward are gone. However, and that's a key point here, if you start with this turbulent mess of a spindle where contractile force is inhibited, then you add the drug to inhibit the opposing extensile force, what you see is a spindle that looks just normal. So it seems that depleting motors individually leads to an incorrect structure. However, depleting both together leads to the correct structure. And that's been known for a long time. However, it's not just that this spindle that's doubly inhibited, missing extensile and contractile forces, looks the same. It also appears to function the same. It enters anaphase. So what's the role of those opposing forces? Why is this system consuming energy for these motors to appear to simply fight each other off and to do nothing productive when they are both there? So in answering this question, we thought, well, these are motors that transport microtubules, so maybe there's some defects in how microtubules move in the spindle. And indeed there are. I mentioned initially that microtubules typically move towards the pole of the spindle in this thread milling motion. And you can see that if you mark a population of microtubules in blue, this mark normally moves to the pole, but in these spindles without extensile and contractile force, this mark moves much slower poleward. So it seems that these spindles are less dynamic in the absence of these two active stresses. We thought, okay, well, since these motors generate force, we tested the hypothesis that these spindles were less mechanically robust without these opposing motors. So here's a normal spindle with nothing removed from it that is being confined under a PDMS device, and we basically squish cells like a pancake to a predictable height of 5 microns. And we exert external forces, artificial force on the spindle to essentially test how strong it is and how robust it is, and how stiff it is. And you can see that the spindle maintains its shape. It gets longer and it's get wider when it's flattened like a pancake, but it maintains its shape. However, if you do the same experiment without extensile and contractile forces, you can see that the spindle gets longer and wider, but it loses its structure. So you can see that these bundles of microtubules that are normally focus and poles here are just focused to nothing. They just end up in free space. So the spindle appears more fragile under force when these opposing forces are gone, which really suggests to us that one role that these opposing forces are playing is to make the spindle more mechanically robust. And you can see this here quantified, where in red are doubly inhibited spindles, and the y-axis is the fraction of time that a spindle fails under this pancake-like confinement. And you can see that without these opposing forces, there is a higher rate of failure, and failures occur earlier in time. So what else is wrong with these spindles that are doubly inhibited? And that's to answer the question of what's the role of these opposing forces. Something very striking that we observed is that while normal spindles appear to go straight in structure at anaphase, spindles in which these opposing forces are gone appear dramatically twisted at anaphase, as if another role of these opposing forces were to keep the system from going, to make sure that it goes straight over many, many microns and doesn't twist itself up. And something here for background that I tell you is that many motors in the spindle and in other cytoskeletal systems walk in a chiral way. So they walk around the microtubule rather than walking on top of a microtubule. And these movies are basically what you'd see if you started at one spindle pole and you traversed the spindle to all the way to the other pole. And you can see that in these doubly inhibited spindles at the bottom here, the bundles dramatically twist. And if you quantify this helicity, which is basically the number of degrees that a bundle will traverse for each micron in this pole to pole distance, you see that this helicity is consistently negative left-handed. And that it, yes.
So you're saying many motors have this helicity when they move over the microtubule?
Some do, yeah.
Yeah, and so do you now think that causes, is that opposing, is that preventing actually the helicity you get without these motors, or is it now the remaining motors that induce it in the double inhibited spindles?
Yeah, that's a great question. We don't know the answer to this question. That's a big part in the discussion of this paper that's on bioRxiv now. Yeah, we would love to know the answer to this question. Because of data that
does the helicity, the direction, the handedness of it, does it match with what motors do, or is it opposed in the opposite direction?
So the motors in the spindle, some have left-handed, some have right-handed. Okay. However, because they're walking, some on parallel, some on anti-parallel, you need to do quite some geometry in your brain. Mm-hmm. But it ends up that all the motors are consistent to make the spindle left-handed, although some of them are right-handed, but because they walk in different directions and so on. Yeah. So in principle, that could give rise to this. However, what we think is that the motors that we deplete, so two models like you stated, either when you deplete these models, you give more space for these other motors that are more chiral to act, or you make the spindle less torsionally rigid. And the latter is what we believe, because we have evidence that I'm not fully showing you here, that spindles are less rigid in the absence of these two motors. Mm-hmm.
Sorry, I also remember data from Eva Tolic that shows that the wild-type spindle also has chirality.
So wild-type spindles, so if you look at here, wild-type spindles have about 1 micron per 1 degree per micron in the cell types that she's looked at. In our cell type here, it's basically 0. Mm-hmm. Okay. And you can see half the bundles are left-handed and half in blue here, and half are right-handed. And some of Eva Tolic spindles, which are human spindles, but in different cell lines, they have small left-handed twists. So around 1 degree per micron. And here it's about 6 microns, so it's much more dramatic. So this you just see on a microscope without any fancy analysis. It's just very clear, But also all of the bundles have the consistent chirality. So it's a very similar phenomenon. It's just much more dramatic now once you remove these opposing forces, which suggests to us that these opposing forces, one role was to not only make the spindle linearly more stiff, but torsionally more stiff as well. That's the model we put forward. Yeah.
Okay,
with limited evidence at this stage, arguably. Yeah. So, and these two particular opposing motors do not appear required for force balance in a linear pole-to-pole axis, right? I showed you that spindle basically doesn't change shape or size without them, but they appear required for force balance in a rotational axis. But how exactly these two motors would make the spindle stiffer is not clear. And then the last defect that we saw without these opposing contractile and extensile forces is that the spindle actually makes way more mistakes. So in red, again, are these doubly inhibited spindles, and in blue are control spindles. And you can see here what's called lagging chromosomes. So it seems that these opposing motors make the spindle mechanically and functionally more robust. Lucas was asking kind of like, okay, how does this come about? We don't know this yet, but I'll pitch something here. So in a normal spindle on the left here, you have opposing motors. If you remove these opposing motors, the spindle is less dynamic. Its microtubules are also less organized, which the latter of which I did not show you, but which we found. And there are two major consequences of removing these two motors. One is that the spindle is more mechanically fragile in anaphase, and that at anaphase, it is all twisted up and it makes more segregation errors. So how do the things on the right stem from removing motors? What we propose is that this disruption, so the spindle being less dynamic, the spindle also having different mechanical properties, which we did not quantify in any way, but the spindle being more compliant, we propose is what gives rise to this mechanical fragility and this functional fragility of the spindle. And why are we excited about this? So the question that Lucas raised essentially, how can motors that are stepping in a chiral fashion on the nanometer scale give rise to micron scale structures that are achiral or nearly achiral? So that's a big question that we're excited about. Another outlook here that we're excited about is the following. In the biochemical world, we've known for a long time that there are active opposing processes like kinases and phosphatases that don't just burn energy and fight each other off, they actually provide added robustness. For example, in cell cycle control. Or mitochondria fusion and fission is not a waste of energy, it's thought to give higher quality to mitochondria. And here we're proposing a similar idea in the physical world, where opposing motors in the spindle, this opposing active processes, would be consuming energy for added mechanical and functional robustness, which we propose is analogous to what people have known for a long time in the biochemical world, that robustness comes at a cost of energy consumption. So that's it. Putting everything together, what I told you in this talk is basically three ways in which the spindle can be robust and dynamic by reinforcing its center here, by locally dissipating force, and what I spent most of the time describing is by using opposing forces to promote its mechanical and functional robustness. And the folks who did the work, so Lila here really spearheaded the motor work. She's fantastic with help from another student, Nathan, and then Pooja and Alex did the microneedle manipulation work. So I'm happy to take any questions.
All right, Sophie, thanks so much for the great talk. So we have a first question coming up from Marilene. Marilene, please go ahead.
Yeah, well, thanks a lot, Sophie. It's really beautiful. I mean, you said in the beginning, it's inspired by the experiments by Bruce Nicholas, which were done in cells where it was easy. Well, I think it was never easy then, and it's probably much harder now. I mean, I don't know anybody else who's able to do this, so it's really amazing, and lots of questions. And so on the last part, so what is intriguing to me that when you remove the two opposing forces, you still get some pole focusing and you still get the bipolar organization. So there's another layer beneath, I suppose, another force balance that is still there. So do you have any idea what else you would have to remove to, maybe too much, but yeah, I have this idea, but it still works afterwards. So there's probably another pair below that does that.
Yeah, that's a great question. So your first point about Bruce Nicholas, when I started postdoc 15 years ago, I took a plane and I went to meet Bruce. And he told me that in basically all his time doing this, he never killed a cell. So the cortex of these grasshopper spermatocyte cells appears to be super compliant, and cell death is not a problem. And I was able right there and then to manipulate, just after one day of training and not kill cells. And I thought, oh, this is going to be fantastic.
Yeah.
I thought it was going to be fantastic as a postdoc. I'm just going to do this in mammalian cells and connect this mechanics with all the molecular scale knowledge we have. And like, here we are 15 years later. And for some reason that I don't understand, but like nobody I've talked to understands, the cortex of all of the cells that people have tried microneedle manipulation with is so much stiffer than in these grasshopper spermatocyte cells. The reason is, so yeah, I think it's not fair to say that it was easy, but there's something very different about the cortex of those cells versus mammalian cells. So your second question, I removed the slide, unfortunately, because of time, but that's also part of the paper that we just posted last week on bioRxiv. Indeed, you are correct. When you remove these two motors, there are other motors that must allow for the spindle to assemble. And the redundant extensile motor is KIF15. And there were many, many previous hints of this in the literature, which is another kinesin. And we know this because if we deplete KIF15, the spindle doesn't assemble. And the redundant contractile motor appears to be HSET, which is a minus end directed kinesin for the same reason, because if we deplete it, the spindle can't form itself. So there are redundant layers. And thinking in the big picture here, like why would not only the spindle like build itself using opposing motors, but why are there so many layers of redundancy is another question that I'm interested in.
Yeah, so there's no role remaining for dyning independent of NUMA, for example. So you think.
so this is something very interesting that a significant fraction of my lab is working on, and I don't know the answer at this moment. So it's clear that dynein does things without NUMA because the phenotypes that we get depleting dynein and NUMA are different. And dynein has been known for a long time to act at kinetochores for cell cycle control.
Yeah.
So if you deplete dynein, spindles will refuse to go into anaphase, which is why in this entire work here, we don't deplete dynein, we deplete NUMA. An analogous question, which is equally or perhaps more interesting to me, is whether NUMA, this protein that tells dynein where to go, does anything without dynein. And we believe the answer is no. But what exactly does it do? So NUMA is a microtubule binder and possible cross-linker. So you could imagine that in addition to targeting dynein, it could do many things on its own.
Thank you.
Yeah, these are two great questions.
Bela is raising his hand. Bela, you want to go ahead?
Yeah, okay. Thanks, Sophie. Great talk, and I love the little graphics you make. So a question on the last thing about the helicity. I was wondering, I don't know anything about how easy mutagenesis is in grasshopper cells, but there are point mutations in tubulin that actually make the protofilaments be helical, either left-handed or right-handed. And I thought that would be a very cool idea to combine that with your idea of the spiraling motion of the motors to see if you can turn that around or counteract it or make it more active.
Oh, that's a nice idea. I don't know how to do this, right? But there are different tubulins that form microtubules, and instead of having 13 protofilaments, have 12 or 15 or 14, and that they have different handedness. I have no idea how to do this experiment, but I would love to do this experiment. I've never thought about it. This is a great suggestion. I have no idea how to do this.
I'll send you a paper. It's on the plant world where you can actually get a whole plant to become helical just by changing the helicity of the.
Oh, that's super cool. I have no idea how in mammalian cells to do this. Tubulin is a rather
it's just a point
essential thing.
So, it's not something we really weigh out.
Oh, that would be super cool.
Okay.
If we can figure out how to do this. Yeah. Mm-hmm.
So we have a lot of microtubule experts in the room. I'm definitely not one, so I'm just going to ask you a bunch of more naive questions. So I was really blown away by a lot of these experiments. One of the first one, actually the first cartoon is about. I was very surprised that as you deflected this one microtubule, you actually didn't see so much deformation going on in the rest of the spindle. It seems as if there's not so much propagation of forces throughout this spindle structure. And I was a little bit surprised because I have this picture of my mind of a more kind of connected network linking the different microtubules together.
So we were also surprised, and the three like baby answers that we got as to why forces are not transmitted over longer distances is one that there appears to be this reinforcement of the spindle in its center, which would help that if forces are locally dissipated is kind of the second answer. And then how exactly the opposing motors would help what you're saying, you know, we don't know. I basically told you our little models here, but yeah.
Okay.
But we were also very surprised, and functionally this has implications because it means that if forces are exerted far away from chromosomes, they may not be felt by chromosomes. And that's basically the current textbook model. Also, in terms of time scales of force propagation, one thing that I did not show you, but which is in this paper, is that these yellow anchors in the center of the spindle, the mechanical anchorage here seems to have a 20-second lifetime, which means that the spindle is protected over 20 seconds, but so the chromosomes would be deaf to short-term forces, short lifetime forces, but they could feel perhaps longer-lived forces over this 20-second time scale of the yellow staple in the middle. And that's exactly what you'd want. You want chromosome to respond to sustained forces, not to respond to short-lived forces in terms of cell cycle control. But both in space and time, I think your point is very interesting. And we were both surprised by this. And I did not emphasize it in this talk, but that's basically the first thing that we saw, like, what is this? Yeah.
Another thing that struck me, I think this was in a movie on slide 12 or so, you were showing two different conditions. One where the spindle was like nicely, let's see if I can find it.
This one here, maybe?
No, I think it was 11, maybe. Yeah, that's where it was, 11. So yes, so when I was looking at some of these different conditions, one of the things that struck me is that in some cases where the spindle remains nicely coherent, fluctuations are extremely weak. While in some of the other cases where the shape of the spindle is really lost, you see much more vigorous fluctuations of the microtubules. I was just wondering what this means. How can you interpret these differences?
Yeah. So on the left here is a spindle where both of these forces are there. In blue here, oh boy, sorry about that. In blue here is a spindle where the contractile force is gone. And this main, so as I said earlier, there are other contractile forces, but the main one appears to be dynein mediated, because if you remove this dynein and pneuma force, you don't even form a steady state. You just form this turbulent mess. So we conclude from this that the contractile force specifically from dynein that cannot be rescued by another contractile motor is essential for forming a steady state. And if you inhibit this motor egg 5, the spindle that used to be bipolar becomes monopolar, because egg 5 is thought to be an essential outward force generator in the spindle. So although these redundant motors are good enough for certain functions, they're not good enough for all functions. That relates to Marilyn's question. And then here, if you deplete both, you get normal looking spindles. So the spindles start out turbulent, right, in the absence of this contractile force. And then you add this drug to inhibit the extensile motor. And then those are the redundant motors at play here. But they can only do their job when these two main opposing motors are gone. Yeah, I'm not sure I answered your question. But.
Well, I guess that was exactly the movie that triggered my question, is comparing the first and the last example. In the last one, you have much larger fluctuations of the microtubules. And I was just
that's what you were saying. Yeah, I'm sorry. Yeah. Yes. And we have not quantified this, but qualitatively what you're saying is true. And that is presumably reflecting different material properties of the spindle in a more compliant, a less stiff spindle. Yeah.
All right, thanks a lot. So I'm just looking around the room if there are any other questions at the moment. If not, Sophie. Oh, there is a question. Go ahead.
I had a question. Yeah, it's a rather naive question about the helicity you observed for the spindle, in the mutants or in the double inhibited case, right? You might have said something about this, but in the end, is there a biological sort of understanding of why that would be bad? Why the helicity should be deleterious? I mean, for the robustness, you showed it's clear.
So that's a good question. So I don't have the answer to your question. So we found two things in anaphase. One is that there are more errors in chromosome segregation, and the other one is that the spindle's all twisted up. It is therefore tempting to say that one reason it makes more mistakes is that the spindle is more twisted up. We haven't shown this, right? But that's one model. How could that be? So one is you imagine that if segregation happens in the state way, there would be few opportunities for entanglements. But if the spindle is twisting itself up, you can imagine that there could be some entanglements. And here, this is just an abstract concept, right? Another thing that you can imagine is segregation is straight. The productive component of force generation is all in the direction of movement. But if the spindle is twisted, force generation, which would happen then in these weird directions, only some of that force component would be in the pole axis of the spindle. These are just like two baby models that we have, but we haven't shown either of these things. But we're very much hoping to to test this and trying to.
It's amazing that you can test these things, and yeah.
Well, I don't know that we can actually. That's why I said we're hoping to test it, but we haven't figured out how to do it.
Yeah.
All right.
Okay.
All right. So we should wrap up now. It's getting late on the side. So first of all, I want to thank Sophie. Amazing talk, and thanks for the discussion. Also, Eduard, thanks, and also our panelists, Marilene, Bela, and Lucas. Thanks for joining in today and making the discussion more lively and interesting.
Thanks for the great questions. These are some of the best questions I've gotten. Yeah.
All right. Thank you all. The next meeting that's coming up will be. Let me just quickly check. It's going to be on the 13th of April with Jennifer Lippincott-Schwartz and Micah Hansen. So hope you can all join for that round. All right. See you.
Thank you. Bye.
Bye.
Thank you. Bye-bye.
Bye. Thanks, Eduardo.